What does localized electron mean? Anybody? Not shared. Not shared. Yeah, just run one, not shared. Yeah. So localized electrons means it's localized on a specific atom or a group. Specific atom is more precise, and you're not sharing it with anybody. Having said this, you can share this electron with another group to make a bond. That's separate from resonance. So what I'm saying is this. Here is OH minus, okay? Here is, okay, this is like a carbocation that you make. This then attacks this, and then you form this thing. This is not resonance. You're actually making a bond there. So resonance is not about breaking bonds and making bonds and to make new bonds. Resonance is you keep the same number of electrons in the compound. You're not creating a new thing. So for example, the electron count here, how many pi electrons do we have here? 2, 4, 6, right? And if we do the resonance on this benzene ring, concerted like this, we end up with this thing. How many pi electrons do we have here? 6. We always have 6 electrons. We never lose the electron count in going from one structure to the other. We just move them, but we do not use them to make an extra bond or to break a bond so we have less electrons. It's always the same electron count. So delocalized refers to electrons you can share between atoms, like these ones. Can I share these electrons like this? Yeah. Why do we say no? We're breaking a single bond. We cannot break sigma bonds. So sigma bonds cannot be broken. Oh, my English is awful. Sigma bond cannot be broken. Pi bond can be broken. Sigma bond cannot be broken. Okay? Not broken. So you cannot move sigma bonds. That's one. So what you have to realize is, can you move electron pair? Do you have one or pi electrons? Electron pair or pi electrons. That's always what moves. We never move a positive charge. We're only moving the electrons from one place to the other, and those electrons come from lone pair or electron pair or a pi bond, and we're moving them somewhere else. They move. So if you have a flexibility of moving these, then it's a delocalized system. You cannot move electron pairs like, for example, right here, CH3, CH3, CH3. Here's the lone pair. Can we move this lone pair towards this bond? People say no. Anybody else? We get this. What's wrong with this right here? We are breaking the octet rule. We cannot break the octet rule. Yes, there's a lone pair that I said you can move lone pairs about, but moving this lone pair and making this a double bond creates this, and this breaks the octet rule. So, octet rule must not be broken. Now, special notice, by going over. So you cannot have 10 electrons, 12 electrons, etc. You cannot have this. 8 electrons is the best. You cannot go over. Going over is unacceptable. Having said this, you can go under 8 electrons, and I'll show you that example. So, let's look at these two. This right here is something I was talking about, right? Here is the lone pair. Here is the pair of electrons in a bond. Question is, can we move these and give it to this bond, or can we move this electrons and give it to nitrogen? We can't. There's a couple of rules of breaking. One is breaking octet rule. If we take lone pairs here and then make a pi bond, breaking the octet rule. The other one, if we take this electron pair and give it to nitrogen, or take electron pair and give it to carbon, we're breaking another rule, which is sigma bond rule. We do not break sigma bonds. They're not part of the resonance, breaking the sigma bond. It's not possible. What about here? You see something like a sigma bond, which you definitely can break, right? Then what else do we see? We see double bond, right? Somebody would say, hey, double bond is a pi electron. You can move it. You can move it, okay? I'm going to follow that they could be delocalized. That is true only if you move them, you're not breaking any other rules. So if I move this over here, can I have this really happen? That's the big question. This is a problem, right? This is a problem. There's a problem here. I cannot move it towards sp3 hybridized carbon, or meaning I cannot move this and have more than 8 electrons. This is 10 electrons, this is unallowed. So having said that, you have lone pairs, and having said you have a pi bond, you can't always move them, because you can't break those rules. So here's the example you've seen before. CH3COO minus really is what we call it, but this is the overall structure. You can see how, you can see how you have a sigma bond between this oxygen, this carbon, and then you have a sigma bond between this carbon and oxygen. And then you have these dashed lines. These dashed lines tell you that the electrons are delocalized between these two oxygens. So this is what it means, CH3COO minus. I am moving the electron pair towards something. If I move the electron pair here, that's very nice. This is sp2 hybridized carbon. The issue is, if I make this, what is the problem? This is bad. So what I have to do is, instead of doing that, do arrow A. What I actually have to do is do arrow A and B. So arrow A and B gives me this thing, right? Is that okay? Did I break any rules? Everybody's happy, meaning all the atoms have octet surrounding them, and the negative charge was with one oxygen, and now negative charge is with the other oxygen, and both of these are equally stable. Both resonance contributors are equally stable. So overall, hybrid resonance structure is something like sigma bond, and then these dashed lines or dotted lines, which tells you that the electrons are shared between these two oxygens. And if you use these dashed lines to show a resonance hybrid, you cannot really put minus here anymore. Because at one instance, this is really minus, and the other instance, this is really minus. So both of them are minus at a specific time, and we assign a partial charge to this. So when I say delocalized electrons, I mean you have electrons to delocalize, meaning lone pair or pi bond, but that doesn't mean that you can always delocalize them. You can only delocalize them, meaning do resonance if you don't break octet rules. And if you don't break sigma bonds, then everything is okay, right? Okay, let's try this example that I have here. Okay, rule number 1.